Welcome to a presentation about ionization energy. Ionization energy is the minimum amount of energy required to move one valence electron away from the atom. It is equivalent to the Coulombic force of the atom, but in the opposite direction, and it would be directly proportionate to the Coulombic force. If we look at lithium, we can see that it has 3 electrons and 1 valence electron, which is in the second energy level. It has a certain Coulombic force, which is attributed to the distance it is from the nucleus, and then the nuclear charge. The ionization energy would be the same, but since it needs, the goal in ionization energy is to move this electron away from the nucleus, you need to have the same amount of energy to counteract the Coulombic force. For carbon, there are 4 valence electrons, and it is a certain distance from the nucleus, and there's a certain nuclear charge. When looking at Coulombic force, you look at 1 valence electron. So, pertaining to the valence electron, there's only the nuclear charge and the distance, and that's the same for ionization energy. There are certain trends to ionization energy in regards to the periodic table. When looking at across a period, there's an increase in ionization energy attributed to the increase in Coulombic force that it needs to counteract. Lithium has 3 neutrons, therefore a certain nuclear charge, and then it has Coulombic force. If we look at carbon, which is across the period, it has 6 neutrons, which charge that they have will be given to the one valence electron over the same distance. This is the same energy level. Therefore, there will be more Coulombic force holding this in and more ionization energy required to remove it from the atom. When going down a group, there's a decrease in ionization energy attributed to a decrease in Coulombic force. Same what we went over earlier with lithium is the same here, but for sodium, you can tell that there's a whole new energy level with the same amount of valence electrons, but since it's a third energy level, there's a greater distance. So there will be less Coulombic force holding it in, so there'll be less energy required to remove this, the electron. There are certain exceptions to these trends, which will be displayed. Certain exceptions to the trends in ionization energy in the periodic table. One of these exceptions would be regarding orbital distance. This is seen in the periodic table between beryllium and boron. The valence electrons in beryllium are located in the s orbital. But when looking at the orbitals in boron, there are 3, and they're all in the p orbital. The p orbital is slightly farther away from the s orbital, and therefore the distance is slightly further. So where if we were to look at beryllium, there'd be an r, which would be the same as all the ones before that were in the s in that certain period, which is now different because boron is in the p orbital. Well, its valence electrons are in the p orbital, and it is slightly farther away, making that there a little bit less Coulombic force and then a little bit less ionization energy required to remove these valence electrons. The second exception would be due to Hund's rule, which regards to the arrangement of electrons into orbitals. This happens between nitrogen and oxygen, and then it's constant through the groups below it. So the valence electrons here, there would be 5 because there's an S, which would attribute to 2 of them, and there's a P, which would attribute to 3, and there would be 1 in each of the P's. But if we look at oxygen, there are 6, 2 in the S, 4 in the P, which means there's 2 electrons in the first portion of the p orbital. And due to electron-electron repulsion, since both electrons are negative, they'll move apart. There'll be one electron that's a tiny bit farther away from the other, but there, since it's farther away, it's the farthest most valence electron. Therefore, it would have slightly less ionization energy. In regards to the video, this exception would be as if we move this one valence electron over a tiny bit, and then you'd see that this distance has changed slightly and it has increased. Therefore, there'd be less Coulombic force holding it in. Therefore, there'd be less required ionization energy. Think of in biology when there's a catalyst, how this reduces the required activation energy in a chemical reaction. This is the same thing, but for ionization energy.